Welcome to our presentation for accelerating vLLM deployment through quantization. My name is Michael, and I'll be covering your introduction into quantization within vLLM, and then Robert Shaw will dive into some performance and accuracy evaluations to show the importance of compression and the dirty details there. So we're from Neural Magic, and our mission is to democratize AI by bringing the power of open source LLMs and vLLM to enterprises and users globally. In the next 30 minutes, we'll explore how quantization can significantly enhance the performance of your vLLM deployments. We'll cover the fundamentals of quantization, its implementation in vLLM, and how it leads to faster inference times and reduced memory usage with ensuring high accuracy preservation. We'll give you valuable insights into both those new to quantization and those looking to optimize their existing deployments. So our presentation is structured into 5 key sections that'll help guide your understanding of quantization. So first we'll cover a quick quantization 101, so fundamentals on the concepts and principles there. Then an exploration of vLLM's implementation of quantization techniques. Then we'll perform an analysis on the benefits of quantization activations in addition to the traditional weight-only quantization. Then we'll have an introduction to our framework llm-compressor for creating quantized and compressed models. And finally, we'll have an overview of future developments in quantization that we have planned for vLLM. So first, 101. Let's begin by examining the fundamental operations within an LLM. At its core, an LLM performs a series of matrix multiplication operations using learned parameters. Each of the billions of parameters are represented numerically and stored using a specific number of bits. Typically, high-precision formats such as FP32 or BF16 are used during training and inference. These high-precision formats allow for a wide dynamic range and high accuracy, but come at the cost of increased memory usage and computation time. To illustrate, a single FP32 number uses 32 bytes of memory. In a model of just 1 billion parameters, this translates to 32 billion bits or 4 gigabytes of memory for just parameter storage alone. This memory requirement presents challenges for deployment and inference, especially as you scale up to billions and billions of parameters, which quantization aims to address. So getting into quantization, it's a technique for representing numbers using fewer bits, effectively mapping high precision values to lower precision formats. For example, quantization might map a range of FP32 or BF16 values to int8 or FP8 ranges and formats. This is what the image shows. So it visualizes this concept showing how a continuous range of values at a higher precision can be mapped to a smaller set of discrete values within a smaller precision. While quantization does involve some loss in precision, advanced techniques during the quantization process allow us to minimize this loss to maintain model performance. In some instances, quantization can even act as a form of regularization, potentially leading to slight improvements in model performance, aiding in generalization. The challenge lies in finding the optimal balance between reduced precision for performance gains and maintaining model capabilities. So quantization offers 2 primary benefits, and that's why you should quantize. So the first one is obvious: reduced hardware accelerator RAM requirements. It substantially can reduce your memory usage. For instance, quantizing from FP16 to int4, so from 16 bits to 4 bits, can potentially reduce your memory requirements by 75%, allowing you to host larger and larger models. And then there's the other aspect of accelerating linear layers through reduced data movement, meaning we'll move less data between memory to the compute units or tensor cores, which is often a bottleneck in AI inference on small batch size workloads. And then accelerating through utilization of low precision tensor cores, such that modern GPUs have specialized hardware for low precision computation, such as FP8 tensor cores, which offers you a significant flops advantage. So for instance, int8 or FP8 operations on modern GPUs can be 2 times faster than FP16 operations, just in terms of the flops or compute available. Compounding this with memory bandwidth, effective memory bandwidth improvements means that the improvement can be even larger sometimes. So a key thing with quantization is accuracy preservation, and we work with advanced techniques like fine-grained quantization to allow us to achieve these benefits of quantization with minimal impact on model quality. Fine-grained quantization essentially means applying different scales to different parts of the weights, even within a single layer, preserving critical local information where necessary. This approach often allows quantization to 8-bit or even 4-bit precisions with excellent accuracy while getting substantial speed and memory benefits. So now let's cover how vLLM supports quantization. So first, our goal with vLLM, and most everyone's goal with vLLM, is to build the fastest and easy to use open source LLM inference and serving engine. We achieve this personally by building vLLM's quantization support on 4 key pillars. First, fast inference kernels, obviously for the most popular quantized operations that researchers and the community is developing. Ecosystem compatibility, such that the popular open source quantization formats that already exist and that we make are broadly supported and accepted by the open source AI community. Then providing pre-quantized model repositories, so people have a collection of ready-to-use off-the-shelf quantized models. And then llm-compressor, which is a unified framework for exploring and experimenting with combining various optimization techniques to get the best performance and accuracy. All these components work together to provide a comprehensive quantization solution within vLLM and make it easy for users. So we'll step through each of those things. So at the core of vLLM's quantization support are the custom inference kernels we'll actually be running that we've contributed that are optimized for quantized general matrix multiplication, or GEMS. For activation quantization, most importantly, we support FP8 and int8 formats using cutless kernels optimized for maximum efficiency on modern NVIDIA GPUs. For weight-only quantization, we support W8A16 and W4A16 formats using specialized kernels such as Marlin, which is optimized for Ampere architectures, and Machete, which is brand new, and we've optimized for Hopper and Onward, as we'll be optimizing for the latest GPUs. If you look at some of the benchmarks on the right, some of this validates this. If you look at the one furthest on the right, we compare our FP8 implementation to the baseline PyTorch implementation, and we show that we can get much better performance and maintain that performance while using even more accurate methods like dynamic per token activation quantization, making sure that users can reach their accuracy goals easily without much complication or leaving performance on the table. So these optimized kernels translate directly to faster inference times, allowing you to leverage fully the low precision hardware available. So vLLM integrates various quantization formats used in the open source ecosystem, including popular ones you probably know of already, like AutoAWQ, AutoGPTQ, GGUF, bits and bytes, with many more existing formats in the community already used for weight-only quantization. These formats, right off the shelf, can be natively loaded and run with our most optimized kernels that are already available inside of vLLM, ensuring that you can use them without trading off compatibility and performance. A key feature we can talk about specifically is the automatic conversion of AutoGPTQ and AutoAWQ models to our Marlin and Machete formats. This automatic conversion, while model loading, ensures optimal performance on your GPU, regardless of the original quantization method. This compatibility layer is key, such that users can load their existing models and just take advantage of better kernels as they come along, rather than worrying about needing to re-quantize to make use of the best performance. So, as I mentioned before, to facilitate rapid development, we at NeuroMagic maintain a repository of pre-quantized model checkpoints on the Hugging Face Model Hub. This includes a catalog for popular models such as Llama, Mistral, Phi, now Vision language models. We have multiple quantization levels for each model: 8-bit, 4-bit, weight-only, 8-bit int8 and FP8 activation quantization, even FP8 KV cache quantization, sparsity. We're growing this day by day. And each of those come with examples of usage with vLLM to demonstrate how to use the models. We also regularly publish performance benchmarks so you can understand the use of these models under various workloads. And then accuracy evaluations for standard tasks to report the accuracy preservation. These pre-quantized checkpoints enable quick comparison of different quantization levels on the same fixed model, allowing you to select the optimal trade-off for your use case. We're continuously expanding this repo based on community feedback, our latest research findings, and of course the latest model of the week. And lastly, what I'll cover is llm-compressor, which is our unified framework for creating quantized models optimized for deployment with vLLM. It supports a different range of compression techniques, including various algorithms such as round to nearest, GPTQ, which uses second-order information for improved quantization, AWQ, as mentioned before, for activation-aware weight quantization, smooth quant for smoothing activation so they can be more easily quantized, sparse GPT for inducing sparsity in the model weights for better compression. And then after you've applied each of these algorithms, we can then save the compressed models in an actual compressed format on disk in many different formats. Like I mentioned before, W8A8 for your FP8 and INT8 activation quantization, W4A16 or W8A16 for quantizing just the weights to lower precisions, and 2,4 sparsity for storing weights and parameters that have inherent sparsity, like for more extreme model compression. The key flexibility of llm-compressor and the composability of all these algorithms and techniques allows users to experiment and determine the optimal quantization strategy for their specific model and specific use cases. Of course, alongside this, we have best practices in there, so you don't need to experiment, and you can hopefully just get on with your deployments. So coming up next, Rob will take the lead in diving deep into the impact here.
Yep. Thanks, Michael. So I'm going to talk about some real-world impacts of quantization and make the case that everyone should be using activation quantization when they're deploying. So hop over, Michael.
Yeah.
Yeah, sure. So in terms of understanding why activation quantization, the first thing we need to do is understand where time is spent when a model is executing. So the chart on the right effectively shows the per layer or the different operations in Llama 3 8B during an inference pass. And the pink bars are what's called the linear layers. And what we can see is that most of the time for reasonable batch sizes is spent in reasonable sequence lengths is spent in these pink linear bars. And the taller bars are showing the amount of time that's spent when the model is running at FP16, and the shorter bars show the model running at FP8. And so the point of all of this is, with activation quantization, is to take the most expensive part of the model and cut it in half. And to understand why activation quantization, I wanted to explain a little bit of what happens in one of these linear layers. As Michael mentioned, the linear layers are matrix multiplications. They're gems. And any gem is, the time it takes to execute any gem is determined by 3 variables, n, k, and m, which are the shapes of the various matrices that are being multiplied together. And so when we look at a large language model, the n and k variables are very, very large. We have massive weight matrices that we need to load into the SRAM and multiply by the activations, and these are fixed. But M, which is the shape of the activation matrix that we're multiplying by the weight, is variable and often very small. So to understand this, most will understand that for LLMs, we have a prefill phase and a decode phase of inference. In the prefill phase, M can be very large. We might have a prompt of length 8,000 or 4,000, and that will make the X matrix have a shape of 8,000 when we're passing it in. But for decode, and especially low batch size decode, M can be very small. For batch 1 decode, M will be length 1, and we'll be multiplying a very large matrix times a very skinny, in the batch 1 case, and actually a vector, not a matrix. And this completely changes the dynamics of how the gem will respond in terms of the overall amount of time that it takes to execute a single operation. So this M variable is very important in determining which quantization scheme to use and how the gem will react. And so to understand why activation quantization, I first wanted to explain what drives the latency of a gem operation. And to do this, you have to understand how a gem kernel works. Basically, at a really, really high level, what happens is the weights are sitting in the GPU HBM memory. And to execute the computation, we move the weights from HBM into the on-chip memory, feed it into the tensor cores, and do the multiplication, and then write it back out to HBM. So the amount of time, or the latency of a gem operation, is driven by A, how long it takes to move the weights from HBM into the SRAM, as well as how long it takes to actually execute the tensor core flops. And these variables, the bandwidth, as well as the tensor core number of flops, are constants on the GPU. So an A100 40 gigabyte, for instance, has 1.5 terabytes per second of bandwidth from HBM to SRAM. On an H100, this is something like 3.35 terabytes per second. And we can see one of the ways that quantization can help us is since we have less weights to move, since we've compressed from FP16 to FP8, there's less data that has to move from HBM into the SRAM. And so when we have small m, when m is really small and the memory bandwidth becomes the bottleneck, how long it takes to move things in and out, quantization can help to accelerate by just reducing the amount of data that needs to move from HBM into the SRAM. And then in addition, as Michael mentioned, modern GPUs, in particular A100, H100, have lower precision tensor cores that simply offer more floating point operations per second. And so on an H100, the FP8 and int8 tensor cores have 2 times the number of floating point operations per second that they're able to execute as compared to their FP16 counterparts. And so if the activations are quantized, we're able to use these lower precision tensor cores and increase the number of operations that we're able to do per second. So you can see how quantization can help both of the phases of a gem kernel. A, reducing the amount of data that needs to move through the memory bandwidth, and then in addition, increasing the number of flops that we're able to execute. Now, one thing Michael has kind of hinted at is that there's 2 types of quantization that we support in vLLM. One is weight-only quantization, which is very, very commonly used in the open source ecosystem. Simon gave me a stat the other day when we looked at the vLLM usage stats, which is something about 20% of total vLLM usage hours are running with quantization enabled, which is great. However, when I looked at the details of the stats, most of the time is actually spent doing weight-only quantization, which is not the right thing to do. Because the way that the weight-only quantization gems work is that we move the data from the HBM into the SRAM compressed. So we take advantage of the reduced data movement. But to actually do the computation, we dequantize the weights in the SRAM and then use the FP16 tensor cores. So we're not actually taking advantage of the additional flops that are available on the GPU. Whereas with the weight and activation quantization, if we quantize both the weights and activations, we're actually able to take advantage of these lower precision tensor cores, which enables us to not only reduce the amount of data flowing from HBM into SRAM, but also allows us to leverage the tensor cores that have more floating point operations per second. And so we're able to improve both of the bottlenecks that exist in a gem operation. And so most of the ecosystem is doing weight-only quantization, which I'm really happy about because we've contributed a lot of it and it's great. But we really, really recommend that users take advantage of weight and activation quantization because of these fundamental reasons I just described. And really why weight 888 is specifically what I just spoke about, which is in an LLM inference server, we see both large M, so that weight matrix, that activation matrix, there's certain iterations in the batches that will have large m, which are compute bound. And so most of the time when m is large will be spent doing flops, executing in the tensor cores. And then the low batch size decodes, when m is small, these are bandwidth bound operations. And so most of the time will be spent in this data movement from HBM to SRAM. And what we see when we do an analysis of an actual LLM inference serving workload, we see that you get a mix of really, really low batch sizes. In this chart I have on the right-hand side, we can see there's a bunch of batch iterations where we have 1 to 5 tokens that we're processing, but we also have a large number of iterations where we get high batch size, high M, which means we need to be able to accelerate both this memory-bound regime and this compute-bound regime. And this is exactly what activation quantization does, as I sort of spoke about before. And so to give you a little bit of real-world data on this, I wanted to talk about some of the key metrics that we use to analyze the performance of an LLM inference server. There's really 2 key variables to consider. The first is time to first token, which is the latency to generate the first token in the batch of a request, and time per output token, which is the inter-token latency, effectively how long it takes to generate the next token. And typically we measure these variables as a function of queries per second, the amount of load on the server. And these charts here demonstrate how the various quantization schemes respond to load. So the left-hand side chart shows the time per output token of vLLM running Llama 3.1 7dB on 4 H100s with 550 input tokens and 100 output tokens per request. And what we see is on the x-axis is the number of queries per second that the server is being hit with, and the y-axis shows the mean time per output token per request. And what we see is at these really, really low batch size, these really low QPS ranges, the mixed precision, the wait for A16, the blue line, gets the best latency. When we don't have too much load on the server, the mixed precision does really, really well. It gives us the optimal latency. And the reason for this is at low QPS, we're spending a lot more time in this low batch M decode phase, and we're not having as much time in the high M prefill phase. But as the amount of load on the server increases and the queries per second that the server is facing goes up, we can see that the latency of the wait for A16 model shoots up because we're not able to accelerate this compute bound regime, and actually we have a performance penalty associated with the dequantization. But the red line, which is activation quantization, we can see is faster than the FP16 inference across all of the across all of the QPS regimes, and enables us to serve more users on the same GPU infrastructure. And as a rule of thumb, for a 70 billion parameter model, typically what we see is the same overall time per output token when running the FP8 model on 2 GPUs as compared to running the FP16 model on 4 GPUs. And so using activation quantization, we can dramatically shrink the overall amount of resources that we need to execute the model. So I hope you all understand activation quantization is where it's at. int8 for Ampere, FP8 for Hopper. These are really the things that you want to use if you're running an inference server and care about reducing the overall cost of the deployment. But what about accuracy? How does quantization impact the accuracy of the models, especially in this activation quantization regime that's so good for LLM inference serving and offline use cases? And there's an element in the open source ecosystem that quantized models are less good than their FP16 counterparts. And I'm here to say that this is not true. And importantly, as Michael mentioned, one of the things we've worked really hard on in vLLM is to enable fine-grained quantization to be able to have accurate model checkpoints. So in particular, one of the ways we can have fine-grained quantization is to use more scales. Basically, when we're quantizing a weight, effectively what we do is multiply the quantized weight by a scale to convert back and forth between the dequantized version and the quantized version of the weights. And a simple, obvious strategy is to use one scale per weight and one scale for the activation matrix. This is called per tensor quantization and is not very fine grained at all. And as you might expect, it's hard to represent the full range and handle all the outliers, especially on the activation matrix when we're dealing with per tensor quantization. But PyTorch scaled MM only supports per tensor quantization, and you have to in a fused way. And so you'll face a significant performance overhead if you try to use more fine-grained quantization without our specific kernels. So one of the things that we enabled in vLLM with our custom Cutlass kernels is to have performant fine-grained quantization. And specifically, what we enable is channel-wise scales. So we can do one scale per row of the weight matrix and per token activation quantization. So we have one scale for each individual token in a sequence. And this enables much finer grained quantization. We're able to handle outliers much better and still have really, really performant inference because of the custom kernels that we've enabled that are targeted at this specific case. And so when we look at evaluations, at Neural Magic, we have built FP, our model repository that Michael was talking about, and our int8 and FP8 activation quantization models we evaluate in two ways. The first is looking at the Open LLM leaderboard, which is a really simple evaluation that's very quick, things like MMLU, GSM8K, et cetera, which are fine, but they're not particularly challenging tasks. And so recently, we've been a lot more focused, especially with some of the pushback from the open source community on the Llama 405B FP8 models, to pick the hardest possible evaluations. And in particular, we've started to standardize on Arena Hard Auto. Arena Hard and Chatbot Arena is kind of the gold standard for instruction models in the open source ecosystem. And Arena Hard is the hardest possible tasks from those, the Chatbot Arena. And with Auto, there's about 500 prompts that are automatically evaluated by GPT-4. And what we can see is that the FP8 models get almost the exact same scores as the BF16 models, and the int8 models are very, very close to their BF16 counterparts. And so we definitely have been really focused on these more challenging evals and have been seeing that with our fine-grained quantization, we're able to keep the accuracy very, very high of these models, and really believe that this is the right way that everyone should be running inference. And you can use llm-compressor to do it. I'm going to skip through these because we're running a bit low on time. Please check out llm-compressor on the vLLM GitHub for some examples of how to create FP8 and int8 models for your use case. But I wanted to hit a little bit on our roadmap in terms of where we're going. Obviously, we've gotten the FP8 and int8 support in vLLM into a really good place. But in terms of new areas that we're exploring, 2-4 sparsity is another operation that we're really, really excited about as the next frontier of optimization in vLLM. Just like the lower bit tensor cores that we talked about, NVIDIA GPUs and AMD GPUs have 2-4 sparse tensor cores, which means 2 out of every 4 weights are 0, that offer a 2x compute speed up over the FP8 dense tensor cores. And so we at Neural Magic have been working on creating 2-4 sparse foundation models where we prune Llama with this 2-4 sparse format, which should offer us additional speedups that accelerate both the low M case, the memory bound case, and the compute bound case as our next wave of optimization. We're working on combining 4-bit weights with 8-bit activations through our Machete kernels. And another area that we're very excited about is the next generation of NVIDIA GPUs, Blackwell, will have FP4 and FP6 tensor cores. The FP4 tensor cores will offer 2x the flops of the FP8 tensor cores. And so we're very excited to work on this for the next generation of NVIDIA GPUs, which will allow even more optimization. It will definitely be a challenge to quantize the activations, especially to FP4, but it's something that we're very excited to work on, both from a research perspective in terms of developing the quantization methods, and in addition, from the kernel perspective for getting the performance acceleration. So thank you all very much. I know this was a very technical topic, but we're really excited about quantization in vLLM, and please feel free to chat with us after or reach out to us in the llm-compressor repository if you have any questions for how to take advantage of these optimizations. Thank you.
All right, so we should have time for some questions, and please raise your hand. I'll go down here first, and then second.
Yeah, I have a question. So, like, you mentioned that like you quantize the linear layer, but from my experience, like when you quantize the linear layer, you introduce quant and dequant. Like sometimes, like I find that the engine actually slows down by introducing quantizations. How do you deal with that, or you kind of like fuse like the linear layer with the activations after that, so reduce the amount of overhead introduced by quant or dequant?
Exactly. So the kernels that we were this is for. So you're talking about with the weight-only quantization. So two things here. We talked a little bit about the different kernels that we have implemented in vLLM. So the center chart here is looking at the mix precision. So this is the weight-only quantization, where basically the weights are quantized, but the activations are not quantized. So to do the multiplication, what we have to do is up-convert the weights to FP16 and then pass it into the FP16 tensor cores. So what Marlin, this kernel, does is it moves the weight from SRAM into DRAM compressed. So we're reducing the amount of data that has to move from the, from HBM into the SRAM. And then we're up converting on chip and then running the FP16 tensor cores. So the kernels are handling the overhead associated with dequantizing. And we're doing this very efficiently in a pipelined way inside of the kernel. And there's a lot of care and magic associated with making that happen really, really fast. So for the mix precision, that's what these kernels do, is hide the overhead of dequantizing by doing it on chip. And ultimately, this works out pretty well for low batch size. But as you can see from these charts, like the overhead associated with dequantizing makes the performance worse for wait for A16 when we get to these higher QPS ranges, because the overhead associated with dequantizing the weights is really, really high when we start having longer prefills. So that's what I would say about the mix precision. For the activation quantization, we have to quantize the activations dynamically. So basically, I think it's the green here, the green in this chart. Basically, the green in this chart, I think it's the green. No, it's not. It's the yellow. The yellow in this chart is the overhead associated with quantizing the activations. Because in each layer, we're going to take the inputs in FP16, quantize them to int8 or to FP8, and then do the FP8 gem. So there's some overhead associated with quantizing and dequantizing the activations. And what we're doing to get rid of the yellow is we're integrating torch.compile, and we're building what's called a graph level optimization system through torch.compile, which enables us to rewrite the graphs and actually fuse those quant and dequant operations onto other operations that exist inside of the model. So this is not yet complete and has been a very long-term project associated with integrating torch.compile into vLLM, but that's a forward-looking optimization that we actually just got the first pass to do this working earlier today. But we're going to be working on putting this into production in vLLM over the course of Q4 to eliminate the overhead, eliminate more of the overheads on activation quantization, which are these yellow lines, which I guess my chart is gone. But yeah, the yellow part of those bars.
Yeah, you see that because I also do the same for my company. Yep. But do you that like do it automatically with torch compile? Like, are you saying you are able to do those like all fusions just with torch compile?
No, it's with custom kernel. How about let's talk about this offline so we can get into more detail.
Yeah. Go ahead.
Thank you for your presentation. I have one question. Do you have any recommendations for fine-tuning for quantized models? Do you have any methods for this particular quantization, and how fine-tuning should look like? Is it better to fine-tune a model before quantization or after? And what's second question, sorry. What data sets you use for quantization, same as a model was pre-trained on, or any recommendations on this?
Yeah. Typically, you're going to want to apply the quantization after you've trained the model. And so, in terms of our stack.
Yeah, we're not going to be able to show the.
Oh yeah, I can't show the slides. In terms of our stack, like Neural Magic, we create a model repository of quantized models, like instruction-aligned versions. But the point and like why we made llm-compressor and why we open sourced llm-compressor was to enable users who have fine-tuned their models onto specific use cases to use our tools to create quantized versions of their model. So the quantization will happen after the model has been fine-tuned, and you can use the llm-compressor framework to apply the algorithm, serialize the models, and then load them and run them in vLLM. The only exception to this is if you wanted to, for instance, take advantage of multi-LoRa deployments in vLLM, like let's say you trained like 5 or 6 different LoRa adapters on your model, and then when you wanted to take advantage of the feature in vLLM where you're going to deploy 5 or 6 different adapters on the same model, in that case, you might actually want to fine-tune the LoRa adapters onto the quantized model backbone, and then when you go to deploy, you will obviously use the FP8 model as your backbone and then attach the LoRa adapters on top of that. But that's kind of what I would say about the fine-tuning setup is like if you're just fine-tuning a model as usual, apply the quantization after. If you're doing LoRa-based approaches where you're going to have multiple adapters on the same model, then you should fine-tune the LoRa adapters on the quantized model. There are some other methods called like quantization-aware training that you can use to recover a little bit more accuracy. This is in kind of like a beta stage in llm-compressor. We haven't really found that we've needed it so far because the post-training techniques, as I kind of showed, have been recovering pretty well. But if for some reason you did want to try to do QAT, this is something that we have nominal support for in llm-compressor, and we're working on productionizing a bit more. And then in terms of data set, for the instruction-aligned models, we have a few generic data sets that we use to calibrate. In particular, we use, and I should probably stop. We use, an UltraChat data set. But if you have a fine-tuned model that's in a specific domain, you should definitely use that data set to calibrate the same data set you use to train to calibrate. And you need like 2,000 samples or so it's not too big. But we can also talk more after. So, thanks everybody.
Okay, thank you.